The outputs could be same for different inputs, but we never get two different outputs for one input. That's kind of the rule. And here's an example. Here they simply put like a simple model. Um, so in the first row, you see the number of seconds. In the second row, you see the number of miles. So how they form this table is um, we have whenever we have a lightning, after that we hear the thunder. So they, I mean, this is like a really simple model. They determine the number of miles a person is away from the lightning by calculating the number of seconds after the lightning they hear the thunder. So if you hear the thunder after the lightning after 5 seconds, that means you're 1 mile away. If you hear the thunder after 10 seconds after lightning, then that means you're 2 miles away, and so on. So it's a simple model. You may in real application you may have a lot of different factors, but they just made this simple model to explain the function. So that represents a function. You have inputs. You determine the number of seconds that it takes to hear the thunder, and then according to that you determine the number of miles that you're away from the lightning. So we call this a function, and you have exactly one input and you have one output, but for each input you have exactly one output. And as you can see, to get the output, you divide the input by 5. We write it in the form y equals f of x. And it reads like this, for example, f of 5 is 1, f of 2, f of 10 is 2, f of 15 is 3, and so on. We call x to be the independent variable and y to be the dependent variable because y depends on x. You find x and then you divide it by 5 to get y, number of miles. And the notation is like this: f of 20, for example, they just put one example. F of 20 is 4, f of 25 is 5, and so on. All the meaningful inputs is what we call the domain, and all the outputs is what we call the range of the function. I'm going to go in that detail in upcoming examples. And I put this nice diagram, which explains that x is input, f is the function's name, and y is the output. That's how we denote it. Now, how many ways do we have to represent the function? We have 4 ways: verbal, numerical, symbolic, and graphical. I put all of them in the next page according to this model. How do we write it verbally? We just say divide x seconds by 5 to obtain y miles. So like in order to obtain the output, you divide the input by 5. That's it. That's how you explain that in words. The numerical representation is what we did as a table. See, this is like a different table, but according to the model at the top page, that works. You divide every input by 5 to get the output. As you see, numerical representation is more like a realistic one because that's how you really form the functions in real life. And then you just simply convert it into a symbolic formula to get more information about that particular problem. But this is more like a finite set of numbers, which simply forms a table to explain that function. That's what we call the numerical representation. The next one is a symbolic representation. So that's like whenever you have f of x, input x, the output will be x over 5. So like if you plug in 20 to be x, you will get 4. If you plug in, for example, 4 for x, y will be 0.8. It's like that formula. This is the one that we work the most with the actual functions in math. But that's how you figure out that connection. You can form a table and you can try to create the best function that fits with your model. I will talk about that in a future video. That's what we call actually regressions, but yeah. And this is how you graph it. Simply plot the points and draw the line. That represents a line. And here you can pause the video and take a look at this example for a couple seconds. X squared plus 1 is explained is a symbol, is a formula, is a table, is a graph, and is within word, in an kind of like explained in words. So just pause the video and check this for a minute. Okay, now we go into some examples. Now the first one is, I put the formal definition. A function is a relation in which each element in the domain corresponds to exactly one element. So every input produces just one output. But you may have like same output for different inputs that work. For this problem, they first asked like expressing words, how f acts on the input x. So you see like what happens is whenever you have an input, and for this one, you square it and then you add 6 to it. So we just write it in this way with words. Just write square um, then add then add 6. See, that's how you explain it in words. Whenever you have an input, you square and then add 6. That's part A. Now for part B, what we need to do, f of 2 is you plug in 2 for x, so it's going to be 2 squared plus 6. So that's 4 plus 6, which is 10. I just want to say if you plug in f of negative 2, you will get the same number, negative 2 squared plus 6. Negative 2 squared is 4, so you get 10. I would like to say this. It is okay to have the same output for different inputs. That's still a function. But what we don't want is whenever you have an input, we don't want to have like 2 different outputs. That's not allowed for a function. And all these type of formulas that we use in basic math, they're functions. They produce like one output if it's given in the form f of x. Now look at this one, f of negative 1. F of negative 1 equals to negative 1 squared plus 6, which is going to be 1 plus 6, which is 7. Then finally, when you look at f of square root of 7, that's square root of 7 squared plus 6. Square root of 7 is 7 plus 6, that's going to be 13. And this is part B. Now part C, folks, domain, it says all the meaningful inputs. So meaningful input means in here what type of risk. For example, if you have 1 over x here, you can't plug in x equals 0. So in order to have something undefined, you may have a fraction or a radical. We will see that in future examples. But in this case, you can plug in everything. Anything that you like can be x. Like you can plug in 1, 2, 3, it doesn't matter. All the possible inputs. So domain of this function is simply all real numbers. We just write it as all real numbers, or we just write it this way. We just write that negative infinity to infinity. Now, if you want to find the range now, just be careful for the range. You see you have x squared plus 6, and that's your output, and x squared is greater than or equal 0. So that means x squared plus 6 will be greater than or equal 6. So that means like this really, and this is your what we call y, the second coordinate, this one, f of x. We represent the outputs by y coordinates. So in this case, y needs to be greater than or equal 6. So that means we're looking at the set of all y's such that y is greater than or equal 6. This is the range. So if you write this down, it starts at 6, so it will be 6 comma infinity on the number line. This is how you get this one, because you see the outputs really start at 6. The smallest possible value for the outputs is 6. And when we see the graphing in upcoming videos, or if you look at the graph, that could be like that could be seen in a better way on the graph. And let's do part D here. It says put like a machine diagram. So it's like you may put that box. You have here you have the input. Your X is your input. This is part D, by the way. You have the input X, and then you have square and square and add 6. So that's what you apply in here. Like that goes into the machine, and then the output will be simply, as you see, x squared plus 6. This is the output. Okay. So I hope this example is clear. This is how you get the machine diagram and find the domain and the range. And let's go to the next example. So this is simple. You try to do some computations. You plug in, for example, find f of 2. That's going to be 2 times 2 squared plus 5 times 2 minus 1. So that's 4 times 2. It's 8 plus 10 minus 1. So that's going to be 17. We'll look at f of 0. It's going to be 2 times 0 squared plus 5 times 0 minus 1. So that's going to be, you see that's 0, so it's going to be negative 1. So I'll look at f of 4. It's 2 times 4 squared plus 5 times 4 minus 1. See, I simply plug in 4 in the formula. So that's 16 times 2 is 32. Because you know this is 16 square 4 plus 20 minus 1. So it's going to be 51. You may use a calculator to do these computations as well. So f of 1 of 2, f of 1 over 2. So it's going to be 2 times 1 over 2 squared plus 5 times 1 over 2 minus 1. Now this is 1 over 4, and that's like 2 times 1 over 4 is 1 over 2, so that's going to be 0.5. Plus this one will be 2.5. Is it 5 over 2? Minus 1, so it's going to be 2. This is how we do it. You simply plug in the numbers into the formula given, that's all, and then compute it. Okay, now let's take a look at this one. This is what we call a piecewise defined function. So it has some conditions. So it produces an output depending on what you plug in there. Like for example, 1.5. Take a look at 1.5. If x is 1.5, which category it fits into? Like whenever you have t of 1.5, t of 1.5, which one should I use? Now look at this. 1.5 is between 0 and 4. See, I need to use first function. So that means like use x squared minus x plus 1. So it's conditional. Like that 1.5 goes into the first interval, so you need to use that one. So it's going to be 1.5 squared minus 1.5 plus 1 equals 2. Let's use a calculator. So here's my calculator. So I'll put 1.5 squared and then minus 1.5 plus 1. That's equal to 1.75. 1.75 is what I got. So for example, you want to find t of 10. Now you need to use the second one, because don't forget 10 is greater than or equal 4. So you check it in which interval the number, the input fits into, and then you use that function. So I will have 3 times 10 plus 1 over 10. See, this is like 30. This is 0.1, so it's going to be 30.1. And then the last one is when you plug in 4. Now, guys, 0 is less than or equal 4 less than 4, or 4 is greater than or equal 4. One of them should be correct. And if you see, the first one is wrong because 4 is not less than 4. But the second one is correct because that includes the equality. 4 is greater than or equal to 4. So I need to use the second one for this. So whenever I look at T of 4, that's going to be 3 times 4 plus 1 over 4. Now 1 over 4 is 0.25, so the answer will be 12.25. So I hope this example is clear. So let's move to the next one. So in this one, we're gonna talk. I mean, it's clear from even the word, but the net change, the net change of a function is simply the change of that function between those two inputs. That's it. So the net change is the difference between inputs. So it's like when you want to find the net change, you simply plug in those two values and subtract the outputs that you get, but in order. So -1 to 2 small to large numbers. So for this one, what I'm looking at is I'm going to find f of 2 minus f of -1. If you like, you can compute them separately. Like, what is f of 2? It's 2 to the third plus 5. 2 to the third is 8 plus 5. It's 13. Then f of -1 is -1 to the third plus 5. So -1 to the third is -1 plus 5 is 4. So this net change will be 13 minus 4, which is simply 9. That's the difference. That's the net change. Now, next problem, what if you have what if you just plug in some like letters into your function? Now, the first one, like whenever you see A, guys, you just put A instead of X. That's it. It's that simple. Like you have, for this one, you have 3 times A squared plus 5. It's that simple. For this one, it's the same thing, but this time you'll put A plus H. So it's going to be 3 times A plus H squared plus 5. Of course, we can do more because you can use FOIL to expand this. Like if you look at A plus H squared, this is simply A plus H times A plus H. You're doing the FOIL for this. It's going to be A squared plus AH plus HA plus H squared. And this level, we just assume these two are same, so we got A squared plus 2 times AH plus H squared. You maybe saw this formula from a lower level algebra class. So let's apply that. It's going to be 3 times A squared plus 2AH plus H squared. Plug that for A plus H squared and then plus 5. So if you distribute this, you will get 3A squared plus 6AH plus 3H squared plus 5. So we're going to be using this part B when we solve part C. This is, guys, what we call the difference quotient. It's really an important concept in math, which actually calculates the slope of the secant line joining 2 points. But this is more like a general type of formula, which will be used in upper level math courses, which will be helpful because that really defines one of the most important concepts in math. So this is what we call the difference um, difference quotient. Just check this. Difference quotient. Now in this one we already computed the first one. You know how to compute that one from part B. So I have 3a squared plus 6ah plus 3h squared plus 5. And it says minus f of a. This is f of a plus h. We have minus f of a from first part again. 3a squared plus 5. And the whole expression divided by h. Now, folks, you see this 3h squared will cancel by 3h squared in here, and you can distribute that negative to both. So, and that 5 will cancel by this negative 5. That will be negative 5 because that's going to be distributed in there. So, in here you can factor out an h. You can factor out an h. From the first term, once you factor out an h, you got 6a. Plus, if you factor out an h from here, you got 3h. And at the bottom, I have h. So every time we try to, we can cancel this h. You can do an algebraic operation in here. You can do, for example, factoring out, or if there's a subtraction, you do like subtraction. But whenever you simplify the top, you should be able to factor out an h. And that h will cancel by the h at the bottom. So our final answer for this problem becomes 6a plus plus 3h. I have something with my mouse. Let me fix that one. So this is the final answer. So let's take a look at this. I hope this problem is clear. That's how we find the difference quotient. Now let's take a look at this problem. In these problems, now you have some restrictions. You have some fractions. What do I mean by those? Guys, if you have a radical expression, whatever you have under the radical should be greater than or equal 0. Okay. So if you have a fraction a over b, then the denominator should be different than 0. So these are all important stuff in this way. For example, when you write a function in this radical in here like a, like part a, you have to make sure that the expression under the radical x minus 3 should be greater than or equal 0. That puts a restriction on your domain, that you cannot put any number in here. For example, you cannot plug in 0. That will make it negative. You cannot plug in 2. That will make it negative. The expression under the radical under the square root negative. It's not defined. So that means we have to plug in, for example, here values larger than 3. And we can see that this x minus 3 should be greater than or equal 0. So x should be greater than or equal 3. So this shows that the domain of f should be all real numbers x such that x is greater than or equal to 3. So that gives you the interval 3 comma infinity. That's how you solve it when you have a radical. If you have a fraction like b, part b, like g, in this case the denominator can't be 0. So first set it equal to 0. I'm sorry, this. So if you look at 8x minus x squared, if you set this equal to 0, then you can factor out an x. And we got 8 minus x equals 0. So x is 0, or we have x is 8. So we have to exclude these numbers. We have to exclude these numbers. Exclude them. So that means on the number line, like it's if you look at the domain of G, you write it in the set builder notation, it's all the x values such that x is not 0 and also x is not 8. If you plug in 0 or 8, it doesn't work. The denominator becomes 0. So on the number line, how do we write this down? So I need to take out 0. I need to take out 8. So that's negative infinity and that's positive infinity. Folks, easy way is you go from negative infinity to 0 with a parentheses and start after 0 with parentheses because we don't know the number after 0. Don't say 1. What about 0 0.1? 0 0.001? You don't know that. So that means here we write it in this form. Negative infinity to 0 with parentheses, not included. Union 0 to 8. Oh, I'm sorry, not infinity. 0 to 8. And the union 8 to infinity. That's how it works. So this is how you write that that domain. Now, the last one is so simple, but let's take a look at that last problem. If you look at the last problem, which is part C, you know, like you have a radical, but also it's at the denominator. So you have 4 minus x this time greater than 0, since square root of 4 minus x is at the denominator. You cannot make it 0. If it's 0, it doesn't work. So in that case, you can put x onto this side. I add x to both sides. These two will cancel, and you see we have 4 is greater than x, so that means x should be less than 4. So in that case, the domain of the function h becomes as follows. All x values such that x is less than 4 as set builder. In other notation, it's negative infinity up to 4 with a parentheses at 4. So these are some problems about the domain. Don't forget, as I said, you have two restrictions. It's like if you have a radical, whatever inside the radical should be greater or equal to 0. If you have a fraction, the denominator can't be 0. These two are the ones. So that's why when we talk about the domain, we mean the meaningful x values that we can plug in. For this, for example, for part C, 4 is not a meaningful value. If you plug in 4, it makes the fraction undefined. I mean, the last problem that like convert 40 degrees Celsius to degree Fahrenheit. I mean, it's here use an appropriate function. You can write f of c equals, it was given as like, you can take a look at that formula. It's 9 over 5 times c plus 32. So this is how you convert degrees Celsius to degree Fahrenheit. So you can use this formula. So I'm going to find f of 40. That's the question. It's going to be 9 over 5 times 40 plus 32. If you compute this, it's going to be 8 times 9 is 72 plus 32. So that's going to be 104 degree Fahrenheit. That's how you do that conversion. So I hope this section is clear. Thanks for watching. Bye.